Steinhauer here, welcome back. We are moving on from the sun to talk now about all of the other stars in the universe and how they work and how we know what we know about them. We're going to be skipping around between chapters 17, 18, and 19 for the next few classes. We're going to start though with 19. But before we even get to any material, let's just look at some stars. Here we have a beautiful star field. And I want you to just take a moment and look at these stars and think about all the things you might want to know about them. And also think about what kinds of things you can know about them just by looking at this image. And so that's basically the next two questions. What properties of these stars, again, moving back at this picture, can we measure directly? And what can't we measure directly, but might we want to know? So let's think about that first question first. What properties of these stars can we observe directly? There's really only three of them that we can measure directly from this image. Let me just write them down quickly. What can we measure directly? We can measure their brightness, we can measure their color, and the only other thing that we can really measure is the position of the stars in the sky, location. That's pretty much it. You might say, and some people do when I show this in class, well, I can see that some of those stars are bigger and other of those stars are smaller. That's actually not true. Almost every star in the sky is so far away and so small compared to that distance that we cannot resolve them, meaning they all appear as points of light. So yes, when you take an image like this, some of them appear larger, but that's simply because the light that we're getting more light from those stars, and it's bleeding into more and more of the image, or more of the pixel of the digital image that we're using to show this. So yes, a lot of these red stars appear bigger. They may be bigger, but we're not seeing them as bigger. They're just showing up as brighter. The brighter stars appear larger in this view. In fact, all of these stars are point sources. We cannot tell how physically large any of them are, actually. Okay, what else might we want to know about all of those stars? This is a limitless list. There is no end to the things that we want to know about those stars. Go ahead and write a few of the things down, though, that you might want to know about those stars, and then we'll come back and make the list together. Okay, I'm going to make an incomplete list, but obviously there's lots of things that we want to know about these stars. We want to know their mass. We want to know their age. We want to know their size, how big they are. We want to know their composition. We want to know their temperature. We want to know their motion through the galaxy, their velocities. We want to know if they have planets. We want to know if they are alone or in a binary system. I'll call that multiplicity. So, and that's just the start. There are 100 other things that you could write down that we want to know about these stars. The goal of the next few classes is to lay down how it is we can determine things about these stars and what and how that's done and what the theory is behind those observations. One thing I didn't mention here that's really important, and perhaps the most fundamentally important because it plays into lots of other things, is distance. Let's go back and look at this picture. You've got, again, a whole field of stars, and just looking at them, we have no way of judging what the relative distances of these stars are. It might be that a star like this is much brighter than a star like this nearby because it's intrinsically brighter, because it's more luminous, or it might be that those stars have exactly the same luminosity, intrinsic brightness, but that the one that appears brighter to us is simply closer to us. In fact, there are lots of properties of stars and objects in the universe, like luminosity and physical size that we cannot know until we know the distances to those objects. And so distance is an extremely important and actually very difficult thing to measure in astronomy. We don't have meter sticks that stretch all the way out to distant stars. We have to be more clever about how we're going to measure distances to those things. So that's the first thing we're going to talk about, is distance. It's one of the most fundamental, difficult, and important quantities to measure in all of astrophysics. And it is a big reason why there are large uncertainties in certain parameters in astrophysics, because until recently, we haven't had a good ways of getting actual distances to objects. So how is it done in practice? Well, there's only one geometric way to get distances to objects outside the solar system. And it's a method known as stellar parallax. Okay, I'm gonna ask you to do an exercise before we get into the stellar parallax that just demonstrates parallax in general. Stick out your thumb in front of your face and close one eye and find some small thing in your room or wherever you are that you can cover up with your thumb. Okay, now once that's covered up, change the eye that's open. Close the one that was open and open the other one. You'll notice that your thumb moves, that it's no longer covering up that thing you were covering up. Repeat this exercise by moving your thumb closer to your eye, and you'll notice something happen about how far your thumb moves. You should see that the closer your thumb is to your eye, the more it seems to move, the more it is displaced from the object that it was covering up to start with. This is an effect known as parallax. Basically, things that are nearby appear to move relative to background things if you can see them from two different vantage points. This is in fact why we have eyes on either sides of our heads. We have two different vantage points, one from each of our eyes, and this gives us, in our local view, a measure of the distance to things. We can judge distances based on the difference in positions that one of our eyes see as compared to the other. How can we do this in astronomy? What is the two? Obviously, our eyes aren't far enough apart to be able to judge distances to nearby stars, right? It's good to maybe 10 to 20 feet around us, which is evolutionary wise the most important part to understanding and being able to judge distances accurately. But it's not nearly as big a baseline as we need to judge distances to stars. But fortunately, we happen to be on a moving platform. That moving platform is the Earth, and the Earth travels around the sun once a year, right? And so 6 months, if we're in January, we're on one side of the sun. 6 months later, we're very far away from that. How far away are we? Well, 1 astronomical unit is the distance between the Earth and the sun. So between January and July, we're 2 astronomical units difference in position in space than we were 6 months previous. That's a pretty big baseline. And it's big enough that with powerful telescopes and still very sharp measurement tools, we can actually begin to measure the parallax angle for nearby stars. So here's an example where we might see in January, this star appears against the background stars over here. It's going to be way over here. And in July, we see this foreground star, this nearby star, moved well over here with respect to those background stars. By measuring the distance that it's moved between January and July, we can use some geometry to get the distance to that star. Before we get to that geometry, I want to show you a short video that shows an animation that shows how this effect works. Here we're going to see the Earth going around the sun in the foreground, and in the background you're going to see the stars, and you're going to see some of them moving more than others. Now this effect has been exaggerated a lot. The stars don't really move this much, but it's going to give you a sense of how this actually works. So here we go. The sun's moving around the Earth's moving around the sun, and as it does, you'll notice that you can almost tell just by looking at it which stars are in the foreground and which stars are in the background, because our brains are in tune to be able to see this motion and interpret it as distance. Here is another animation showing exactly the same thing as before. You've got the constellation Orion in the upper left-hand corner. I don't know if you can see the 3 belt stars there. Anyway, this is showing the same thing. Again, the nearby star, all of these stellar parallaxes have been exaggerated, in this case by a factor of about 1 million. They're moving much smaller than this. But again, your brain sort of intuitively sees the distance that's caused by this parallax. It kind of looks like you're moving your head back and forth among the star fields. And that's exactly what's happening. So the stars that are moving the most are the ones that are the closest to us. And the stars that are moving the least are the ones that are furthest away from us. We can codify this with an equation. And it is one of the simplest equations that we will use all semester. And that is, the bigger a star's wobble over the course of a year, the closer that star has to be to the Earth. And that is simply d equals 1 over p, where d is the distance and p is the parallax angle. Now, this is one of those equations where you have to use the right units in order to make it work, right? And in this particular case, remember, like p squared equals a cubed in Kepler's laws, p had to be in years and a had to be in astronomical units. This is the same way. Distance in this case has to be in a unit called parsecs. And parallax angle has to be in a unit called arc seconds. So those aren't units you're familiar with, probably. So let's take a few minutes and try to understand what an arc second is, and that will lead into understanding what a parsec is. So start with an arc second. You're probably familiar with a couple of different units of angular measurement, the radian and the degree. Let's define those first and then talk about how an arc second is related. So here's a circle. And you're probably familiar that one full circle is 360 degrees. And you're probably also familiar with the radian, you may or not be, the radian unit in which a full circle is 2 pi radians. So that's a full circle. Now, so a degree to start with is a very small unit of angular measurement, right? If we were to, let's say, break this circle up into degrees, there would be 360 of them all the way across. I'm probably not even drawing them close enough together. Each one of those is probably several degrees, but you get the idea. A degree is a very small unit of angular measurement around the outside. If we take one of those degrees, which is already pretty small, and break it up and zoom in on it, let's say here it is, take one of those degrees and zoom in on it, and we break that degree up into 60 subunits. Each one of those subunits is an arc minute. So 1 degree equals 60 arc minutes. And sometimes you will see this written as 60 with a single quote, which is short for arc minutes. So minutes of time are the same as minutes of arc minutes in the sense that they're 1/60th of something. A minute of time is 1/60th of an hour. 1 arc minute is 1/60th of a degree. So that's already a pretty small unit of angular measurement. Now, if you take each one of these arc minutes and expand it out and break it up into 60 pieces, each one of these is an arc second. And so 1 arc minute is equal to 60 arc seconds. So an arc second is 1/60th of 1/60th of a degree, which is already 1/360th of the entire way around the circle. This is a very small unit of angular measurement. So this is going to seem like some strange questions, but let's ask some other questions. How many arc seconds are there in a circle? Well, we know that there in one circle is 360 degrees. And now we can just do unit conversions. How many arc seconds is that? Well, we know that there are 60 arc minutes in 1 degree. The degrees cancel out. If we multiply by the fact that there are 60 arc seconds in 1 arc minute, the arc minutes cancel out and we're left with arc seconds. 1 circle equals 360 times 60 times 60 arc seconds. And that's a big number, 1,296,000. That's how many arc seconds there are all the way around a circle. Or if you like it, an arc second is 1,296,000th of a complete circle. Now, how many arc seconds are there in a radian? Remember, 1 circle is 2 pi radians. By the way, we haven't talked much. What is a radian? Let's actually answer that question first. Let's do a circle again. A radian, it turns out, is if you were to draw a straight line from the center to the outward, that's a radius. And then you were to take that same distance and move around the outside of the arc of the circle, that same amount, such that this line and this line were exactly the same length, then this angle is exactly 1 radian. A radian is the amount around the outside of a circle that you get when you take the radius and stretch it around the outside of that curve. And it turns out all 3 of these are the same. So that's a radian. And it takes a little more than 2 of them, a little more than 6 of them rather, 2 pi of them to get all the way around the circle once. So that's a radian. A circle is, we know 2 pi radians. We also know it's 1,296,000 arc seconds. So 1 radian, divide both sides by 2 pi. 2 pi's cancel out here, and we get 1 radian. And this is actually a number that every astronomer knows because it's kind of important, is 206,265 arc seconds. Okay, keep that number in mind because it's going to be related to what a parsec is. Okay, so here we have the geometry of the stellar parallax. We've got down here the sun and the Earth going around it, and we've got a nearby star here at some distance d, and we've got farther away stars that are over here. So we actually define the parallax angle of a star not to be the complete motion that a star makes over the course of a few months. We define it to be the half of the distance. And that gives us this right triangle, right? We know that this angle is a parallax angle P. That's here. Let's draw that circle. Let's draw that, let's turn that triangle on its side over here and consider that triangle, right? By similar triangles, we know that this angle and this angle have to be the same. And that makes this equal to our parallax angle. That is P, that angle is P. We also know that this distance here is 1 astronomical unit. So this distance here on the short side is 1 astronomical unit. And this distance is d, is the distance we want to know. This is a right triangle. We know an angle on one of the sides. We can get any other angle on any sides, and that's what we're going to do here. So we can use the small angle formula. Remember what the small angle formula is? I'm here to remind you. The small angle formula says if you have a right triangle with a very small angle on this side, which we do, then that angle, P, is equal to the ratio of the short side to the long side. So in this particular case, that becomes P equals 1 astronomical unit divided by the distance to that star. Let's solve this for D. Multiply both sides by D. Divide both sides by P. The D's cancel out over here. The P's cancel out over here. We get D equals 1 AU over P. Now, if P is 1 arc second, This has to be in radians. So P has to be in radians. Well, what is a radian? This is 1 AU. An arc second is 1/206,265th, as we just decided, of a radian. So this is 1/206,265 radians. So 1 over this in the denominator brings that up to the top. This is equal to, the radians kind of goes away now, and this is 206,265 astronomical units. If a star has a parallax angle of exactly 1 arcsecond, then its distance will be 206,265 astronomical units. And that is, by definition, we define to be 1 parsec. A parsec is 206,265 astronomical units, which is a much more useful unit for measuring distances between stars. In fact, it's pretty similar to a light year. If you say a parsec is that, then this is about 3.26 light years. A little bit larger, 3 times larger than a light year is a parsec. And this is where the name parsec even comes from, right? Parsec, parallax angle, arcsecond, parsec. That is the definition of a parsec. And if you're a Star Wars fan and you're remembering that scene where Han Solo is bragging about how fast the Millennium Falcon is, and he says it can make the Kessel Run in 12 parsecs, in under 12 parsecs, that's a total misuse of the word parsec. He's using it as a time when in fact parsec should have been a distance. It is a distance. A unit of parsec is a distance. It's a useful distance for measuring distances between stars, but it is definitely a distance and not a time. Okay, great. Let's try this equation out for size. How far away is the nearest star? Well, it turns out the nearest star in the sky, the closest star besides the sun to the Earth, is the star Proxima Centauri, and its parallax angle is less than an arcsecond. It's 0.772 arcseconds. So what is the distance to this star? Well, it's a pretty simple formula. We know that distance equals 1 over parallax angle in arcseconds. If we've got a parallax angle in arcseconds, we can just plug it into this formula. If we don't, if we were given it to us in degrees or radians or any other unit, we'd have to convert it into arcseconds before we plugged it into this formula. In this case, we don't have to worry about it. We can just say 1 over 0.772. And if you do that, you get about 1.3 parsecs. PC is the short term for parsecs. So no star in the sky has a parallax angle of more than an arcsecond, and no star in the sky is closer to us, besides the sun, than 1.3 parsecs. That's the closest one to us. All other stars in the sky have smaller parallax angles and larger distances. Okay, until recently, the Hipparchus satellite had the best parallax angle that had ever been measured of any stars. It was a satellite whose sole purpose was to measure parallax angles of lots and lots of stars. And it did hundreds of thousands of stars to unprecedented accuracy. Until recently, the most accurate that there were. And the best parallaxes that Hipparchus was able to come up with had an uncertainty of about 0.001 arcseconds, which is astonishingly good. 1 milliarcsecond. So the stars with the smallest parallax angle that we actually believed have quite a bit more than that parallax. You need about 3 of these uncertainties before you start to believe it. And so the best that Hipparchus was able to do was to get to a star that had a parallax angle about 0.003 arcseconds. So what is that? How far away does that give us? D equals 1 over P. If P is 0.003, we can just plug it in. 1 over 0.003, and you get a number that is 333 parsecs. Or if you like it in light years, you can multiply by 3.26, and you get a number that's about a little over 1,000 light years. That's pretty good, right? We're getting a large way away from the Earth. But how does that compare to the galaxy? Well, it turns out the galaxy is a pretty big place. We'll talk about the galaxy later on, but the galaxy is basically a bulge with a disk, and the sun is about 2/3 of the way out of that disk in the disk of the galaxy. We're about there. And it turns out that the distance from us to the center of the galaxy is about 8,000 parsecs. So this, even the best parallax angles that we had a few years ago, only gets us 333 parsecs away. That's not even 1/20th of the way to the center of the galaxy. If I were to draw a region around the sun in the galaxy that we could actually measure any parallaxes at all, it would be a dotted circle that looks kind of like that. That's it. That's all we could measure with direct parallax. There are other ways to get measurements to objects, but they involve knowing something about the objects themselves and having some theory about the objects themselves. This is the only geometric way to do it, and until recently, this was as far out as we could go. Now, I keep saying until recently. Why is that? Because another satellite was launched several years ago that has been taking data now for many years, which is doing even better, far better than Hipparcos did. It's called the Gaia satellite, and it is measuring, and hasn't come out with its full catalog yet, but we've got incremental versions of it. It will measure parallaxes 100 times better than Hipparcos did, down to 10 micro arc seconds. Remember, micro is 10 to the -6. So 10 micro arc seconds is 10 to the -5 arc seconds, which is an amazingly small unit of angular measurement. And Hipparcos will already has come up with catalogs that have over 1 billion stars measured. We're getting a substantial fraction of the entire number of stars in the galaxy, and it covers in volume and in scope the entire galaxy itself. This is a game changer for astronomy and game changer for telling distances to things, and a game changer for understanding physical nature of structures in the universe. So we'll be saying more about Gaia as we go along. Thanks.